I'm in a field which is slightly different from the mainstream of this workshop. So what I think I will do in my talk is to do a broad stroke survey or tutorial or whatever you want to call it of how deep learning has been applied in computer vision and how it's enabled us to analyze images and video. And I hope that some of the insights and techniques from that will be relevant in other contexts. And I look forward over the next couple of days to talking with more of you about ideas of how that might operate. Okay, so I want to start with actually a newspaper article. This is from the New York Times, 1958. So that's just about 60 years old. And it's kind of interesting because this was from the first neural network revolution. As some of you know, we are right now in the third neural network revolution. So there's the first one from the late 50s with people like Rosenblatt that got killed essentially by Minsky and Pappert's arguments about what these functions could not be computed by single layers. Then there was the second revival, which was in the 1980s, and currently we are in round 3. Okay, but in the first round, what you see in this story, this is obviously I'm not going to read this article out, but what they managed to do was with like a linear perceptron with like very small number of units, they could tell the difference between lines of varying orientations. However, from this, Mr. Rosenblatt said in principle it would be possible to build brains that could reproduce themselves on assembly lines and which would be conscious of their existence. So I do not know whether Rosenblatt said this or the New York Times reporter made it up, but the point here is that hype has been associated with this field, unfortunately, from the very early rounds. So it's not that there isn't genuine progress, but please be aware that it tends to get blown up, particularly in the popular press in this way. Now, so we are now in round 3 and in this round, let's say roughly, I would call this as starting right in the early 2010s. We have had some areas with very definitive advances, and computer vision, speech recognition, machine translation, and game playing are those. The field of AI is a broader field. I mean, that has a long history. I mean, the desire to mechanize many of the activities which we call as intelligent, and deep learning is a part of that. And I'm saying this upfront to make sure that you don't have the impression that everything has been solved by deep learning. We have had particular advances in these, particularly in these perceptual type problems, and image processing and speech are really good representatives of that. Now, I work in computer vision. I worked in computer vision for more than 30 years in a variety of different problems in a variety of different paradigms, and I'm going to focus on that. And to set the stage, I want to sort of talk about what I regard as the 3 set of central problems in image analysis or video analysis. The top one is recognition. So this is usually a categorization. Are you looking at a dinosaur or a pear or whatever? So these are classification problems. Reconstruction, these are basically inverse problems. So this is like the inverse of graphics. So there is some 3-dimensional world which gives rise to a 2D image, and we are trying to recover properties of that 3-dimensional world. It could be depth, it could be reflectance properties, it could be illumination patterns, so on and so forth. And reorganization refers to sort of clustering or sort of finding a set of pixels which belong to a single object. So, and all 3 of these are actually connected to each other. And I'm going to start, this talk is itself going to be in 3 parts. And the first part is going to be more or less about the recognition and reorganization area. And it's all based on discriminative models with neural networks. The second half of my talk, the second third of my talk is going to be about sort of these reconstruction problems. And we'll talk about sort of our mainline ideas on how we get to 3D from 2D images. And then the last part, I'll really get into generative models. Okay. So let's start with this. And I want to give some history here. And this is about how convolutional neural nets came to be. Okay. And we've always, since we're talking about intelligence, it's very natural to think about what inspiration we can get from psychology and neuroscience. And once in a while we get useful ideas, and many a while we get ideas which lead nowhere. Okay. And this is true in other fields where people have tried to mimic biological capabilities. So if you want to build airplanes, you don't necessarily succeed by building flapping. Right? That's not the way, the Wright brothers' success was with fixed wing aircraft, and they didn't really succeed with flapping, though lots of attempts were made in that direction. Now, this is true here between the ideas from neuroscience and cognitive science. Many of them have turned out to be duds, but some have turned out to be successful. And this particular idea has been immensely successful. And this goes back to the work of Hubel and Wiesel, who were visual neuroscientists trying to understand the visual system, initially of cat, later of monkey, but basically the same things work for humans. And they found neurons in the visual cortex, which is this part of the brain, which respond to bars or edges of differing orientation. And they found these cells called simple cells, which could be modeled reasonably well by linear filters tuned to particular orientations. And they also found convex cells, so-called complex cells, which were somewhat insensitive to the precise position of the stimulus which caused the response. Now, and then they postulated that essentially you could have multiple layers of these kinds of filters, and that way you could eventually get to more complex pattern recognition capabilities like face recognition and so forth. Now, based on these ideas, neural network models were proposed back in the 70s. Okay, so Hubel and Wiesel's work, by the way, got them a Nobel Prize in medicine and physiology. This is a paper from Fukushima, who called his approach a neocognitron, and it is exactly based on the experimental findings of Hubel and Wiesel. So you have these layers of there's layers of the neural network with what are simple cells, which could be thought of as filters. And if you see in the title, it says mechanism for pattern recognition unaffected by shift in position. So obviously you want to recognize an object wherever it is in your visual field, so you want to have the same filtering everywhere, so that naturally means convolution, right? And then after a layer of filters, the next stage was like the complex cells that Hubel and Wiesel had found, and the way to achieve that was to have some pooling, some zone in space in which you regard anywhere if it fires, it's okay. And now you replicate this process repeatedly, and this is a paper from 1980. Okay. Now so this is inspired by biology, but then what Fukushima did was that he paid way too much attention to the biology. He wanted a learning rule which was very biologically plausible, and so he proposed various Hebbian mechanisms and so forth. Now we move to the 80s, and now this is the time of the second neural network revolution, and this is where you have kind of the discovery or rediscovery of backpropagation, depending on whose history you want to believe, which is basically this idea that, okay, you want to do gradient descent, there's a differentiable function, so what you want to do is, and you can compute the derivative very efficiently using this backpropagation trick. Apply backpropagation to these networks, and backpropagation was not believed to be biologically plausible. Still, the people who think that this is really what's happening in the brain are a very small minority. Francis Crick wrote an article in Nature in the late 80s which exactly argued against backprop because of, he didn't say it, he said this is not plausible that this is how it happens in the brain. Anyway, but once you apply backpropagation, so now you go into the domain of applied math and you ignore the biology from then on. This is what Jan LeCun did. So this is the LeNet of 1989, and he showed this architecture has these alternating simple cells, complex cells, and he showed it was effective at digit recognition. And this is back in 1989. And now you roll forward from 1989 to 2012, and in a way the biggest advances really have been in engineering. Okay, so hardware, so GPUs, as well as large data sets which enable this. And that's what leads to this revolution of, there's the ImageNet data set and AlexNet, which is the architecture from Jeff Hinton's group. So, okay, so this is the context where I'm coming from, just to try to show how this idea, this convnet idea, arose historically. So, okay. Now what I will do is, in my first part of the talk, first third of the talk, I'm going to talk about how these convnet architectures got applied to solve basic computer vision problems. So if you see, and I'm going to, a lot of the material I'm going to use is from a tutorial which you can download from Ross Kershik. And so there's a lot of the work in this space is, I mean, he calls it the generalized RCNN framework, and I think you can download it and read that. But let me be concrete here. So this is, so typically you can run the convnet on top of an entire image, but that's not what gives you the things you care about. What are we usually interested in? We're interested in sort of the objects in this image. So there are, in this image, there are objects like people and boats and so forth. So you need to mark individual objects, and then you need to say where they are. So there's a bounding box which signals where the object is, and then there is some label like person 0.983. So that means we are saying that there's a 0.983 probability that what is in this bounding box is a person. Okay. So that's called the problem of object detection. And it is not a priori obvious how a convolutional neural net applied to an entire image enables you to get this answer, because we want multiple objects localized, right? Okay, you might be a bit more ambitious. You might not want to just say where there's an object. You might actually want to mark the object more precisely in terms of these are the pixels corresponding to the object. So that's what's called the segmentation, instance segmentation problem. Okay. Here's another problem that we care about. So these are kind of like the canonical, like linear algebra people have standard problems, right? Least squares, eigenvalues, etc., etc. So in computer vision, we have our set of standard problems, and I'm running through that set here. This is another one, which is key point detection, which is that, for example, you're looking at a human and you want to mark locations like left shoulder, right shoulder, tip of the nose, left hip, right hip, etc. So that's a key point detection problem. Here is a generalization of that, where you're trying to estimate sort of the more fine-grained locations in the body. So this is what's called the dense pose problem, and that enables you to sort of recover a mesh corresponding to the object. Okay, and we have had tremendous progress. I mean, and this is the way why the press is so gaga over the field. I mean, in the pre-neural network era, there were numbers were something like 5%. There's some measure of accuracy, which we don't need to get into that precise definition, and it has gone up to say 46. Okay, and so it's like in 2.5 years you've had sort of, you would call it like a 9-fold progress. I mean, when that's a pretty big deal. Now, how did it occur? So it has occurred, and this is relevant to other places where you apply deep learning. And I would say part of the progress has been due to better understanding of the problem. So better modeling of how to capture the constraints of the problem. And part of the progress has been generically using better neural network backbones. So there are, for those of you who are in the business have heard terms like AlexNet and VGG and ResNet. So these are all sort of various neural network, generic neural network architecture. So think of those as like your basic counterparts of your basic computer hardware. Are you using an Intel chip or an ARM chip or whatever? And then on top of it, you have how you use this architecture for your specific task. And both set of advances have been helpful. So let me give you a little intuition about this, because this whole family of approaches, I won't get into all the gory details. Like this is like the first paper from this family. It started out actually from when Ross Kershik was a postdoc with me at Berkeley. And I mean, this line of work has been developed. So basically, if you want to find individual objects, how do you do that? So you can run a network on the entire image, but that doesn't tell you where the person is or where the horse is. So what we did was we had this idea that, okay, first you must have some candidates. So over the image, by some process, you come up with proposals. So candidate bounding boxes. So by some heuristic process, you generate guesses of where there might be interesting locations. So there might be like 2,000 of these. So most of them will be garbage, but a few of them will correspond to real person, real horse, real dog, real chair, and so on. Now what you do is you pull that window out, and now on that window you compute all your neural network features. So basically the computation has to be done 2,000 times if you have 2,000 candidates. And now from those features, at the end you have a classifier which says airplane, person, whatever. Okay, and this worked, and this was responsible for the first early breakthrough at an object detection, that we could get much better numbers with this methodology than we did with more traditional techniques. But this is slow, so this is just repeating that. So we have features that are computed over the entire image, but those are not useful. You need to compute features on each separate window, so that multiplies the work. So this is slow RCNN, if you will. R stands for region, and then CNN for convolutional neural net. And then over the couple of years, people developed better variants. And here is a better idea, which is you have the image, you compute features over the entire image, and then this RPN is like a region proposal network. So you have the job of proposing candidates itself be done by another neural network, right? And so it produces candidates. And now what you do is you pull information out from those interest zones, and then you feed it to something which is going to do the final declaration of, is this a dog, what's the probability? And it also tries to come up, not only does it try to come up with a probability of whether that window contains a dog or chair or cat, but also tries to localize that object slightly better. Okay, so that's the bounding box regressor stage. Okay, so this reduces the computation. You don't have to do a separate, you do the features in one sweep, and then you pull out interesting zones and only for the last layers. And then there are variations on this theme, and as I said, I'm not going to get into this. This is, I think, the last most prominent step in this. It's so-called mask RCNN, and that gives you results of this type, which are I mean, 5 years ago, if who have worked in this field for 30 years, if somebody had asked me, will we get results of this quality, I would have said no. Okay, so these are, you can see the objects have been found, and they are very nicely delineated and so on. So this is kind of the result which has made the entire computer vision community switch en masse to using deep learning rather than the other kinds of techniques, handcrafted features and so forth we used to have. So these are just more results. And okay, this is the summary slide, that we have progressed through better design and then better neural network backbones. Let me use up a few minutes to show something more new. And this is really new in the sense that it's not even published yet. It's on archive from our group in Facebook. And this is trying to solve, this is basically the state of the art on action recognition. So what do I mean by action recognition? So okay, I'll get into the motivation in as action recognition means what are people doing? So right now I'm talking, you are listening, you are sitting, somebody could be running, somebody could be jumping, somebody could be performing a gymnastics maneuver. So that labeling of what activity they're performing from some video stream, that's the task we're trying to solve. And again, this was an area, so as I said, insights from neuroscience and cognitive science are sometimes helpful, but sometimes they're not. But here was another area where we benefited from it. So neuroscience tells us that in fact, there are, the visual system has sort of these two pathways, roughly speaking, sort of the what and where pathway. One pathway where you're recognizing objects, another pathway which has much more geometric information and guides action. And this is related to the so-called parvo and magno pathways of cells, where some are faster responding than others. Again, the details are not super important because we are not going to slavishly adhere to the biology or neuroscience. It's just for vague inspiration, and then you have to justify it on mathematical or engineering criteria. So what we did was that we call this the slow fast style of neural network architectures, where basically you have two pathways, a slow one and a fast one operating in parallel. Slow one is roughly corresponding to what's the parvo or the recognition kind of pathway. The fast one is roughly corresponding to the magno pathway. And so here's the idea. So here is some video clip. So the slow pathway, if you can see, it looks jerky because the frame rate of that is slower. If you're just looking at what are the objects in there, you don't need to be looking at every action every 1/30th of a second. 1 hertz is fine. Okay. On the other hand, so there's a pathway which is doing sort of coarse detection, and there's this other pathway which is looking at the motion signal, but it's going to be low resolution with respect to space. And you see that here, right? So here the motion is no longer jerky. So in this pathway, we are going to have much finer temporal sampling. The other pathway, slow pathway has coarse temporal sampling. You make up, if you're going to have finer temporal sampling, that means you're going to have more data there. You compensate for that by having fewer channels and fewer spatial resolution, lower spatial resolution. So that's the fast pathway and the slow pathway operating in parallel. Vaguely inspired by neuroscience, but at this point you can ignore the neuroscience and just say, here's this architecture, is it going to be any good? And you need to have the information from one pathway feed into the other. And then all the gory details, these are these various parameters. Again, let's skip all this. So you learn filters, some filters which are basically spatial and some which are capturing more the temporal action, the movement and so forth. I'll jump through all this. And okay, the bottom line is that now it's empirical. Okay, how well does it work on standard tasks? So here is a canonical, this is the big challenge called AVA, Atomic Visual Actions. And this is one on where it's sort of derived from movie clips and hand labeling of the actions being performed by all the humans in a scene. And what we find is that this is now the best performing, it's now a state-of-the-art system here. This chart shows on the x-axis there are different actions, so stand, watch, talk, carry, touch, crouch, grab, watch, sing, things like that. And then you see the performance numbers, and the green is what you have got from the use of motion. And you see this trend, which is that the ones towards the left are doing better, the numbers are higher. And that's a standard phenomenon we find. So these neural network deep learning techniques, they really use a lot of data, and they work best when you have tons of data. Now, what we have when we collect examples of categories is that you have some common categories for which you have lots of examples, and then you have other categories where we have very few examples. So there is a long tail phenomena, and the categories which are in the long tail, which are over on the right, basically your performance is low. So this is something which we haven't solved yet in the deep learning community. The problem of what's called few shot learning, when you have very few examples, where humans can do perfectly well, but our computer programs cannot. We kind of need like 1,000 examples for a category to do really well, whereas humans can manage with like 5 examples. And the reason why they can is because they are somehow able to transfer their meta knowledge from other categories, and we don't quite know how to do that. I mean, lots of people are working on that, but it's not so trivial. So anyway, so this concludes the first part of my talk. I'm going to take a little break and switch to the second part. So now, so that gives you a flavor of how detection problems are being addressed in the community. And now I want to switch to 3D. And the reason is that the world that we deal with, so I'm used to dealing with objects at human scale. I mean, most of you are dealing with the stars or the interior of the earth. For me, I'm very dealing with mundane things. The objects which are in my field of view at a certain distance of 10 meters, that's the scale at which I operate. And what we are interested in is, of course, we have access to 2D images, and we want to make sense of the world. So there is this line of work which I showed you, boxes and masks. But this is in a way extremely narrow, right? It's just viewing, it's kind of doing pattern classification. It's saying, taking sets of pixels and labeling them chair or dog. It does not acknowledge at all the true nature of the world, which is that there are objects which are in a three-dimensional space which are being projected onto the two-dimensional plane of the camera. And we want to get at that underlying three-dimensional reality, right? And this is what we should be doing, right? And that's how we'll be able to make more sense of the world, because when I look at the 2D level, an object which has been hidden by another object is broken up into two parts. So suppose there is there's a pole in front of a man, then I see the person as existing as two sets of pixels. This is meaningless. We don't see that as humans. We think of this as a 3D person with a 3D pole in front of them, which is occluding the person. So that's the kind of thing we want. We want to understand the world in 3D. Now, understanding the world in 3D is interesting because, and in fact, the ideas here which may be relevant in other settings, and that's a problem which people in computer vision have worked on for decades, I would say. And there are a bunch of ideas here which are of general philosophical value. How do we see 3D given as just, so your most basic answer will be, oh, the reason I see the world in 3D is because I have two eyes. But this is palpably false, right? I just shut one eye and I can perfectly see all of you in 3D. Why? The reason is because I have prior knowledge. I have some awareness of what people are or objects are. So in fact, when I look at a face in a photograph, I see it in 3D. You go to a painting in a museum and you see it in 3D. You can make the effect much better if you shut one eye and you look through an aperture, but obviously we can see 3D from a single image, and that's because of prior knowledge. You have some prior knowledge of what faces are or polyhedra are and so forth, and you take and what you're trying to do is to consistent from the image, you're trying to make the best guess of the latent variable, which is the 3D object. Of course, we do also make use of multiple views when you have it. I mean, so there is your canonical cue of parallax or triangulation, and we do make use of that. We also make use of other stuff which feels very much like inverse problems. So there's this example I have about shape from shading. So if you have some light source illuminating some surface, then the brightness of a particular point, the light from a particular point coming towards the camera, is related to the surface normal and the direction to the light source and so on. And if we crank through the math there, we may be able to invert the process to recover the surface shape. So that's this idea. So anyway, so what we know is that our ability to see shape or 3D shape is a combination of multiple of these cues. Okay, some very directly related to the signal and some related to the priors. And we have to sort of find a way to make all this work. So let me give you a flavor of how we can do that. So I'm now focusing on object-centric 3D. We want to know for every object the 3D shape. So let me take up one example problem to give you the flavor of how what you will see in a computer vision or machine learning conference these days. So this is a particular paper, but it gives you a flavor. So let's take this problem. So here's a bird, right? Okay, let's say, now do you see it as just flat pattern, or do you sort of imagine this as something like this, right? That's how you conceive of it. Now how do we do that? Okay. You may never ever have access to like a bird which you hold in your hand from which you have built a 3D model. You may never have that. In fact, potentially all you have access to birds are far away. They are not, I cannot capture them and put them into my 3D scanner. I have multiple views like this. Okay? And from this somehow I build an internal model of birds, which is helpful in this previous task. Okay. So how do we do this? Now note that your standard idea, which is, oh, let's use multiple views and parallax and stereo and so on, is irrelevant here, right? Because you don't see multiple views of the exact same bird. You're seeing multiple views of different birds. Okay, there is something Platonic about a bird which is latent, but what you have are specific views of specific birds from which you have to induce something about the general bird. Okay, so right, okay, so let's say we have some key points on the birds and we can segment it out. So this is going to be our task. So our task is, given a single image, this is what we need in the online phase. Eventually, once our system is trained, what we need is a function f, and this function f should have the property that given a single image of a bird, it spits out all of these. It spits out the 3D shape, maybe some kind of a 3D mesh, spits out what's the camera, it spits out what's the reflectors pattern or texture. And once you have all of this, then of course you can run so this is solving the inverse problem, if you will. But what you've learned is a function which can solve the specific inverse problem for this particular image. And of course, once you have that, then you can do all the forward part. That part is trivial, right? So how do we do this? So we have to train this function f. Now, how are we going to train this? We are going to have access to lots of images of birds, but never multiple images of the same bird. So we are going to try to, so we have to try to predict some representation. And the way so the question is, how do you parameterize this? So the way you parameterize this is that you have like so there is some regularization that you have to do, otherwise the problem is under constraint. So the idea here is that there is some mean shape of a bird, and then there are some variations from that, and those will of course vary from one bird to the other, because so there is some learned mean shape, then there is some shape deformation which is relatively small. Okay, and so now what we are trying to do is that there is an encoder stage where, given an image, you are trying to guess the camera, guess the shape, and then and a texture. And okay, so let's forget this part. This part is pretty straightforward. And now we have to have, in our optimization, we are trying to minimize certain losses. So one loss is the reprojection loss. So if you think that there is a certain 3D shape, if I run that model in the forward direction, it better match up with what you think where the key points are, right? And so that's the predicted key point should be correct. So and then the predicted appearance should be correct. But in addition, you need some priors to make this. And the priors, basically we found that imposing certain priors was enough, which was symmetry, right? So the bird has bilateral symmetry. Then there's some priors which is that the shape is relatively smooth. How do you capture that? Well, you go back to differential geometry and minimal surfaces and such, and mean curvature is a pretty good measure to use as something to minimize. And that's it, and that gives you this kind of setup. So note that if you go back, if you want to talk about it in terms of the standard jargon of supervised or unsupervised, this is neither. We don't have supervision in the sense that you have a 2D image of a bird and you have a 3D model of the bird, so you learn this mapping. No, you don't have access to that. What you have is some kind of consistency and some kind of sort of priors. So there has to be consistency, the projections have to be right, and then there is some kind of a prior on mean curvature, symmetry, etc. And this is often going to be the case. The problems are in fact never so cleanly either supervised or unsupervised. There is weak supervision, that's the most common regime, and that's what we have to find ways to use. Anyway, so this gives you some results and pictures. Okay, We can do, now sometimes you may have access to more information. So you might have multiple views of the same object. So then we can learn a stereo machine. I'm not going to go into the details here. I mean, there's some architecture. But the interesting thing here, which I want to point out, is a characteristic of human vision, which is quite pretty, which is that suppose there's a chair way in the corner of the back in the room. I'm looking at it from here. I will see it as 3D, but most of it is basically hallucination, because I don't have, at that distance, stereo is effectively, stereo accuracy falls off as with 1 over z squared. So basically at that distance it's flat. So all I'm doing about when I'm guessing the shape of the chair is because it's remembrance of chairs past, some prior knowledge which is enabling me to guess the chair. And as I approach the chair, this changes. Now I have access to multiple views because I have 2 eyes looking at that same chair. And now the model corresponds to the particulars of this chair. So what you need, by the way, in the characteristics that you have is sort of this smooth absorption of extra information. You start out hallucinating based on priors. As you have more data, as you approach an object, you get that precise shape based on the exact, the closer to the signal and less of the prior. Now this is what, classically that's what Bayesianism is about. It is that philosophy, but sort of instantiated in this setting, and I think that's important to do. Okay, I'm going to move on to another example, and this one is about people. So we want to interpret images of people, and maybe with only a single image. So people are a category we are familiar with. So again, you're going to fall into somehow using some parametrization of humans. And this is, by the way, big business, because as you might guess, if lots of people want to sell you clothes, and if your body shape is scanned in and available, then they can recommend clothes for you. So e-commerce, I mean, people care a lot about having ways of estimating models of people's shape. So okay, so the idea here is we want to estimate the shape of the person. So roughly the architecture of this work is you start with some, you have some image, you're trying to guess the shape, guess the camera. You need to be consistent when you do the back projection. And then you need to have some way of capturing this prior of what is a plausible human. So that's captured here by using this discriminator, which is trying to make sure that in addition to the reprojection loss, you are consistent with the human. If you don't do that, you can build monsters. You have this person which has been guessed, the key points are consistent, but it's not consistent with what humans are like. So you need that kind of a model of what a human is, right, which you can train. Okay, we have moved on from this to be able to infer dynamics. So suppose I just see one image, I actually have a sense of what will happen in the future, and this is trying to show you something about that. What is true, and so how do we train networks like this? So again, so from a single frame we can do a prediction of the 3D shape, but if you have temporal information, you ought to do better, right? So the way we do this is, okay, so the idea is you have video input and you want to be able to do something like this. And somehow the availability of the extra temporal information should make your results better. And you should be able to infer even from a single image. So the way this works is that, okay, you have this machinery that I described earlier for predicting sort of this encoder starting from the pixels to sort of the 3D shape of the person. And now you have this over time, and you have this architecture which the way you train this is, and this is very common for these kinds of temporal problems, you use prediction as a loss. So you don't need to have external supervision. You try to predict what will happen at a certain frame, and you do know what actually happened in the data, so that gives you a loss. This is used very commonly in language and speech, for example. Right? You want to build a language model, you have seen some words in the past, you try to predict what will be the next word. And supervision comes from the fact that you actually have some text, so you know what the next word actually was. So it's like self-consistency or prediction, but you don't need to have a human mark what the labels are. So you train with this kind of a loss. It turns out that you can suppose I give you only one frame. Now this even if I give you a single frame, I somehow imagine my brain runs forward in time, and I sort of see that one sequence, and I sort of think the guy is going to kick the ball next, because I have experience of many previous movies or videos that I have seen, right? So we actually have this ability to hallucinate from a single frame this whole movie clip. Our brain generates these stories. We are prediction machines, and now you can again from that single frame you can predict, try to hallucinate what the movie strip would be like. And okay, I'll skip this part, which is about data, which is but anyway, I'll just show you some pictures. So we are now at this kind of stuff. So this, as you might imagine, this has lots of practical applications, understanding what humans are doing. If you want to assist humans in any environment, you want to know what they are doing and what they want to do. You can use this as a way to train robots, because humans can perform certain tasks very naturally, and then you can have the robot do imitation learning from this setting. And we can try to predict dynamics. So you just have this one frame, and you based on previous experience, you know what will happen next. So in this last part of my talk, this is the generative model, because you saw the first part, the first third of the talk I was basically doing discriminative models for classification. The second part was really how to do sort of inverse problems in this setting where you have some priors. And this part of the talk is really about generative models. And this is very new work. And so instead of like modeling P of y given x, we are trying to just model P of x. Okay. So so there's a classical work on maximum likelihood. Typically you have some form of the probability distribution, but we want to go for implicit probabilistic models. So the idea is this: imagine I want to generate the set of all natural images, or the set of all images of butterflies, or what have you. Okay, and I have lots of, so my problem is going to be the following. I'm going to be given lots of examples. So I'm given lots of images of butterflies. That's what I have as my training available data, samples, okay, examples. And I have this neural network, and this neural network is going to generate the pixels. The input to this is basically samples from a Gaussian. Okay, so maybe you pick a 10-dimensional Gaussian, you generate you draw from that, you pipe it through. So the Z is picked from a Gaussian, you pipe it through, it produces one butterfly. You pick another sample, pipe it through, you get another butterfly, and so forth. So if I have my perfect butterfly image generator, that's what it will do. So we have this multi-layer neural network, and that has high capacity. Now the challenge is basically how to make this machinery work. Okay, so we get different samples by this. So the usual, the classical way of training these models is obviously maximum likelihood, but you don't have an explicit form of the maximum likelihood here. So you need to do something else. So there will be more classical approaches which you could use if you have Markov random fields and so forth. But what the community has been focusing on is, and in between we went through these Gaussian mixture models, VAEs, and so on. But currently a lot of the action is in these implicit models. So the most popular approaches these days are what are called GANs, generative adversarial networks. Okay, and what I'm going to talk about is an alternative to that, and I'm going to motivate it by critiquing why GANs don't work. I mean, there's a fundamental problem with GANs. Okay, so this is standard stuff. Let me explain first of all our approach. Okay. Actually, I think I can explain the idea very simply. Okay, so I have so let's imagine some 2D space. Okay, so we have these squares which are given to you. Okay, so the squares are these are examples. So think of each square as corresponding to one of those butterflies. Okay, and then I have my neural network which produces which I feed it a Z and it spits out some image, and I feed it another Z and it spits out another image, and so on. And what it's spitting out are all these blue circles. Okay, and currently, so basically what's our goal? We have a true distribution which is given empirically by all the red squares. That's the true thing, right? It's empirical, but that's all we have. That's the best we can do. The blues are what I produce by my generative neural network. What I want to do is, ideally, the distribution of the blues should become like the distribution of the reds. That's what I want to achieve. Okay, how do I achieve this? Okay, so what's the most obvious thing you can do? In fact, I think it's surprising, but in fact, the most obvious thing to do, we'll argue, is actually the right way to proceed. So what we want to do is, all these blue guys, what do I want them to be? I want them to be like the red guys. So what we do is, for every red guy, we find the nearest blue guy, right? So you can do this, right? For every red guy, you can. So now what's my objective? So that blue guy now should try to become like that red guy. Okay? So what we should do is to move that blue to be close to the red, and do that for every blue point. So basically, once this process it will never actually ever converge, but if it actually converged, you would be generating only red points and you'd be happy. Now the reason why it will not degenerate is because this is output from a neural network which has a certain capacity, and okay, so it's going to always have some smoothness built in. Okay, so that's the idea. Finds the nearest sample to each data example. Nearest samples are found, and then you pull the sample towards the data example. So the blues are pulled towards the red. Okay, you do this for all data samples, and this just formalizes this. So you just have some distance, maybe the L2 distance, after you found the nearest neighbor, and then you implement this. And so now it turns out that this needs, in the inner loop, this needs solving the nearest neighbor problem, which used to be considered pretty hairy, just in terms of computational complexity, but we have a very fast algorithm for that, but I won't talk about this. So that's it. So what are we doing? Once we have so the cost function is actually this sum of L2 distances after you have mapped every point to the nearest neighbor. And now how do I make the distance smaller? You tweak the parameters of the neural network which generates the data samples. So that you do with SGD classically. Okay. Now compare this with the current dominant paradigm, which is the so-called generative adversarial nets or GANs. This is like a big field. This is like, there are like 5,000 citations to this original paper from 2014. And there the idea is, again, the game is the same. You're trying to get the two distributions to line up, the distribution of the reds and the blues. But the way you do this is that you train a generator and a discriminator. So nothing wrong with training the generator. But there is this discriminator which is being trained to distinguish the samples which are produced from the real examples. Okay. And you have this like a duel between the two. The generator is trained, the discriminator is trained. They both keep getting better over time. And this is like, and this results in really amazingly pretty pictures which are being produced, and everybody is very happy when GANs are like the best thing since sliced bread. Okay. I mean, this is the details of the optimization criteria, but I gave you the intuition. The rest, this just captures it. But okay, but here is the problem with GANs. GANs have a fundamental problem, which is that they are doing the matching in kind of the wrong direction. So I don't have time to go into a bit more detail, but basically what GANs can do is they can drop modes. So they can just not model some aspects of the data. And you can see how that would be, right? So you have a discriminator. So suppose I'm trying to generate pictures of butterflies, and I choose to just generate some butterflies. My discriminator can be quite happy because the ones which it declares as butterflies are in fact butterflies. It's just choosing not to deal with some parts of the space. And that is perfectly allowed in this framework. Okay. So GANs only care about making each sample similar to some data example. It does not care about whether each data sample, in the usual jargon, it cares about precision but not recall. You don't have to cover all the entire distribution. And this is a problem. And so here's the joke here, which is actually pretty pertinent, which is elections should be about voters choosing politicians, and gerrymandering is about politicians choosing voters, right? The other way around. So the directionality matters, okay? And that's basically the difference between the two approaches that I talked about. In the GAN case, what you're doing is the equivalent of gerrymandering. You're choosing which of the data examples you want to try to capture, and then you are happy with that. But this is only a subset of the data. So that's a fundamental problem. So anyway, this is our so mode collapse. This is a well-recognized problem. We are not the first to point that out, but we are pointing out sort of approaches to how to solve this, and then various other things. So you get some other more technical difficulties, but I regard the anyway. And now some results which show that the style that we are advocating does better, so here is so we can now synthesize. So now we have a generative model which can synthesize. You can also do the conditional version of this. So super resolution is I'm just given this blurred image and I want to generate more examples, and conditioned on this, and you can do that. Here's another pretty example. What you're given on the left is a certain semantic segmentation. So the pseudo color codes various categories, and the system is trying to generate various pictures of road scenes which are consistent with that segmentation. Okay, so there is a new work from Yedid, Hoshin, and myself, which is what we call generative latent nearest neighbors, and I will not be able to get into details, but this takes the IMLE idea and combines it with something called GLOW, which is a way to embed examples on the sphere. I don't have the time to do that, but at the end of the day, we've shown that this combined approach can now produce examples. You're generating examples of these MNIST digits, and you get now a quality which is as good as GANs in terms of appearance, but without this problem of dropping modes. And there are ways to measure this with, there are some benchmarks, and I'll show you some pictures of the kinds of generations of face. You can do generations of faces. You can interpolate between faces. So this is like showing off that you have got the manifold of faces from which you can generate examples, and you can also do linear. So this is like going from the two ends correspond to two faces, and you're trying to interpolate in between. Obviously, standard Euclidean interpolation will give you garbage because you'll go off the manifold. Here it's showing that you are staying with valid faces all the way through.